Okay, we are rolling. This is lecture G6, airtightness. Basics of airtightness for buildings, blower door test, and airtightness of the four typical wall construction which we always show. Basics of airtightness. Airtightness is the resistance of infiltration, exfiltration in out of conditioned air through gaps, cracks, openings in the building envelope. Causes of air leakages are pressure differences between the building envelopes across the building envelope, or the temperature difference across the building envelope. Control air leakages, it is necessary to do so due to the energy efficiency, the energy performance of the building and the occupant's comfort. And uncontrolled infiltration, air infiltration, exfiltration could create increase of energy consumption, logic. Health and safety of building occupants, we're going to see that by the wind speed and damaged buildings, building materials. Deterioration of building materials means rotting. Too much humidity in the system, and by that having the building rotting. What do we need to do? Air leakages may contribute to over 30% of the heating cooling costs. It may create some problems with comfort and moisture. So we need to seal our occupant, our conditioned space, which is what we see here. And the unheated basement, an unused roof may be sealed off. I really need to seal this. It needs to be airtight. It needs to be tight so that there's no leakage, so that there's no conditioned air exchange, but also no air getting into the system. As such, these air leakage consequences, thermal, air quality, moisture damage, and HVAC system, so heating system, the last two obviously end up with the energy efficiency. Durability is this one, which has to do with damage, and then indoor environment quality, indoor quality in the means of thermal comfort and air quality are targeted. You can imagine if you have a very good new build building, this ventilation-related heat losses versus transmission-related heat losses is shifting. Ventilation-related heat losses, so if we have an air leakage, this will be additional ventilation-related heat losses. So it's not total numbers, it's actually percentages saying new building, low energy new building, that needs to be sealed very nicely, very well, otherwise you're going to lose a lot of energy, versus, for example, an old building where you have the old timber windows which may still leak, and you somehow need to deal with it, and you actually heat less due to the losses of the building. How do we do this? We need to deal with air exchange rates. Exchange rates are known from the earlier lectures. We need to deal with an CO2 percentage which we need to reduce, and for that an air exchange of about 30 cubic meter per person is required. This air exchange being required could be reached by, for example, the top one, a typical ventilated window. Just entirely tilt the window, open it, and with that have an air exchange of 0.5 till 20 times the volume. Adjustable, medium. Acoustic performance, low, just open the window. Versus, for example, a ventilation through a window with an outer layer of glass, the double facades, for example, which has acoustic protection high, adjustability low, depends on how you deal with it, but still reasonable air exchange. Ventilation flaps, good air exchange, low adjustability, low acoustical performance, so maybe not advised. Then ventilation gap. Nordic countries have this a lot. Denmark, the Netherlands, they have this ventilation gaps to allow ventilation, good to be controlled, good in acoustic performances, still reasonable in the air exchange, so something which is quite advised. And then there's ventilation openings with sensor or pressure controlled, maybe added here. Very good acoustic, low to medium, I would say it depends on how you deal with the system, adjustability, and still a reasonable air exchange as opportunities to ventilate a building to secure and control the needed air exchange. Then air pressure. The tightness of the building envelope is largely influenced by air pressure. A crucial factor in this impact of wind pressure on the the crucial factor is the impact of wind pressure on the windward side of the building, overpressure, and the wind suction on the downwind side, under pressure. So louv and lay, as we say in sailing. So here we see a wind-oriented side of a structure, and we see, okay, there are some leakages because the foil is not perfectly duct taped to the structure of the facade. It's not entirely sealed. You can see that later in some samples. That gives wind pressure into the system, and then the building itself is overpressured, and then the leakage will occur also on the downwind side to balance the wind pressure in the system. And then by that we create this draft in the building, but also the energy losses of conditioned air in the building. The draft in the building is something which is important as well. We have to deal with this one, temperature in here, then velocity, so speed close to the body of the air. We see certain temperature and speed range which we like. Actually, at a certain temperature we quite like some movement of air. It feels cooling, it feels like cooling our surface. But if it gets too much speed, then obviously you see it's uncomfortable. If it gets too cold and too warm, it's uncomfortable as well. So we have to deal with that velocity as well. Everybody knows this. If you have a huge room, a high room with cold outer surfaces like single glazed facade surfaces, you have that downdraft. And this downdraft actually feels uncomfortable. It just feels cold. So I'd like to get away from that point to find a different one. And that's what we have to overcome by designing this indoor comfort in these buildings. How do we rate this? How do we evaluate this? We have this nice tool called blower door test. A blower door test is actually sealing a building, closing every opening, only having the door, blower door, being positioned, and there place a blower, which then sucks air out of this building, and by the volume which is taken out of the building, you can identify how much leakage you have in this building, volume by hour. Volume through the blower door, volume of the building by hour. And this leakage identifies, or this is a good number to identify the leakage, but it also allows you very nicely to identify the locations of the leakages. So this is such a blower door which is brought in position. It's just seals the door and then evacuates the building. And then with a fog machine, you identify the leakages at the building by seeing it penetrating. You identify positions where, say, systems are not brought together nicely, where not sealed well, where the construction site is not dealing with its performances and with its qualities as it is necessary. You're all aware of you need to seal the insulation with a duct tape to make sure that all the screws, all the penetrations which you add to this insulation are covered. And if you don't do, it's going to be identified if a blower door test is executed on this construction site. Same happens, for example, for insulation, especially if we have prefab houses with an inner layer of the gypsum board, for example, and then the sealant isn't done perfect. You identify this draft within this insulation. You also easily can identify, okay, this seems to be a leakage. The wind is brought in position. The main structure is here. The whole thing is sealed, but it obviously didn't work well here. And then by having the blower door, you're able to identify this kind of situations. So how do different types of walls deal with this? With a normal single layered structure, and you can imagine where the one part of the component hits the other part of the system. This gap is always the point where the leakage would happen. This gets a lot better if you have an entirely wrapping, enveloping structure, which we do, for example, with thermal insulation at the outside of an envelope. If you do this at the inside, you can easily imagine, this is where two systems are matching each other, and that needs to be done in a high quality. And if you go, for example, for the ventilated facade, mainly used in the prefab systems, you can again imagine the one system, floor slab, matching the other system, the building envelope. Even if we seal it, all these details need to be airtight at the inside to secure that our building itself is entirely airtight. So what we mainly have to do is we see all these systems, but we mainly have to deal with the the connections between the systems, the joints between the systems, which have to be detailed wisely so that the airtightness could be continued or executed well. The building physics books, which we did on this, the building physics lectures suggested, and a nice booklet which helped us to prepare this kind of content. And again, this is part of the Delft Darmstadt Munich Facade Education program.